Welcome back to your notes on rational functions. And our goal today is to graph all rational functions. And while you're copying that down, I'm just going to change my color back to black. All right, so the most basic rational function we looked at yesterday, and it's the reciprocal function, f of x equals 1 over x. And it's interesting because it's the first time that we get to see asymptotes. The asymptotes that we see are really one of the first times. The asymptotes in this function are at x equals 0 and y equals 0. But we can be more precise than just a basic reciprocal function. And so what we're going to do is define a rational function as the following. We're going to let f and g be polynomial functions. Okay, and we need g of x to not equal 0. Then we can define our r of x, our rational function, as the ratio or the quotient of f of x over g of x. And once we do that, we get a variety of really interesting traits for our graph. So let's take a look at them on the next page. All right, so we'll start with our traits. So the first trait that we talk about are the zeros. And the zeros are your x-intercepts or intercept. So they're also known as x-intercept or intercepts. And we find them when that f of x function, when the numerator equals 0. The y-intercept, as always, is the point where the line crosses or where the function crosses the y-axis. And just like always, we set x equal to 0 to find. But now we have some really interesting things that happen with horizontal asymptotes and vertical and slant asymptotes. So let's take a look real quickly. I'm going to scroll down. All right, and we're ready to go now. So let's consider the fact that r of x was that ratio of f of x and g of x, where f and g were polynomial functions. So what that means is that we can write f of x as a x to the n plus a series of other terms. And we can write g as b x to the m plus a series of other terms. Remember that n and m are the degrees on the base x. What happens with our horizontal and our slant asymptotes is that if n is less than m, so if the higher degree is in the denominator, then your horizontal asymptote is y equals 0. If the degrees are equal, then your horizontal asymptote is the ratio of a over b, the coefficients on the leading terms. And if n is greater than m, a slant asymptote occurs. And you find it by using polynomial or synthetic division. Vertical asymptotes and holes occur together in the same way that horizontal and slant asymptotes are kind of joined together. So vertical asymptotes occur when there are zeros in the denominator. As long as the x value isn't a 0 of the numerator. Okay, so as long as there isn't a number that makes the top and the bottom equal to 0, then you'll have a vertical asymptote. But if there's a value that's a 0 for the numerator and a 0 for the denominator, then that common factor crosses out. Okay, and then we have a hole. So a hole occurs when a common factor reduces. Okay, so let's take a look at our first example. We want to give the zeros, the y-intercept, the equation of the asymptotes, and the domain and the range in interval notation, and of course we want to graph it because that's the most interesting part. The first thing that I always like to do is to factor the numerator and the denominator. So the numerator obviously doesn't factor because it's linear, but the denominator, well, it doesn't have a common factor, is linear, but also does factor, and so we get -2 times the quantity x plus 3. So our zeros are when the numerator equals 0. So when x plus 4 equals 0, the value of x that makes that true is -4, and then y equals 0. The y-intercept occurs when you plug in 0 for x, so we would have 4 over -6, which reduces to -2/3. We have a horizontal asymptote at y equals -1/2 because the degrees of the numerator and the denominator are the same. And then we have a vertical asymptote at x equals -3 because that's the value that would make that 0 in the denominator. So we'll go ahead and graph this. Make this a little bit thicker so that we can really see our axes. Because our y-axis is, or our y-intercept is so close to our horizontal asymptote, right, -1/2 and -2/3, I'm going to kind of zoom in a little bit. And so I'm going to count each block on the y-axis. I guess we could do it on the x-axis as well as 1, or each 2 blocks as 1. Whenever you do this, make sure you note it so that I know that you've kind of zoomed in on the picture. All right, now we are going to graph our asymptotes. I always like to graph them first. Whoops. I'm going to make them blue. All right, so our horizontal asymptote is at y equals -1/2. And our vertical asymptote is at x equals -3. The y-intercept is 0, -4, so it's right here. Excuse me, the x-intercept is 0, -4. The y-intercept is 0, -2/3. And then you can plot a variety of points to discover that the graph does something like this and something like that. Be very careful to make sure that your graph doesn't look like it's going to cross the x or y, the horizontal or vertical asymptotes. All right, let's move on to the next example. Okay, and then the last thing we need to do is write our domain and range. So our domain are the possible x values, and really we have every possible x value except -3. So we'll write it -∞, -3, not including the -3, union -3, comma, infinity. And then our range, the same type of thing occurs except that we don't want -1/2 for our y value, so we'll exclude it in our interval notation. And there we go. Okay, So again, we'll factor it. Negative 4 in the denominator x times the quantity x minus 3. So then we can find our zeros, which would be when the numerator equals 0. But negative 4 is never going to equal 0, so there's not one. And then our y-intercept, which would be when we plug in 0 for x, but then we get 0 in the denominator, so there's no y-intercept. Our horizontal asymptote is going to be y equals 0 because the highest degree is in the denominator. And then our vertical will be at x equals 0 and x equals 3 because we have 2 zeros there. Okay, and then now we can go ahead and graph this. So let's make our axes a little bit thicker. And this time I don't think I'm going to zoom in. We'll leave each block as 1. But we will change it to blue to make it a little bit easier to see. So our horizontal asymptote is at y equals 0. Whoops. All right, get there. And our vertical asymptotes are at x equals 0 and x equals 3. If we pick points, say we pick an x value of 4, then we'll get negative 4 over 4 times 1, so negative 4 over 4, also known as negative 1. So that gives us that point right here. We know that that happens. To the left of our leftmost asymptote, we can do the same thing. If we plug in negative 1 for x, then we get negative 4 over negative 1 times the quantity negative 4. Which gives us negative 4 over 4, which is negative 1. And then we have this graph. And then we're left with what's in here. So if we pick a value for x of 1 and 2, either one, let's do 2, then it's negative 4 over 2 times negative, negative 1. So that's negative 4 over negative 2, which is 2. The same thing happens with 1. And then if we pick a half to see what's going on inside, we'll get 1.7 repeating as our value. So we'll graph that. And that's what our graph looks like. And this point is 1.5, comma 1.7 repeating. All right, so now we can go ahead and write our domain and our range. Our domain is far simpler than our range because as we look across for our x values, we'll include every x value with the exception of our asymptotes. So we'll have negative infinity to 0, union 0 to 3, union 3 to infinity. Our range is slightly more difficult because as we look at our y values, we have all the negative y values up to 0. But then there's a gap essentially in this space right here. So then we have to make sure that we don't include these before we start back up at 1.7 and continue up with our y values. So to do that, we will write negative infinity, comma 0. We're not going to include the 0. And we'll join it with the set where we do include the 1.7 repeating and go to infinity. All right, last example. again, we want to factor as soon as possible. So we'll factor the numerator, x minus 7, x plus 1 over x minus 2. Our zeros are going to be at 7, 0 and negative 1, 0. The values where the numerator equals 0. Our y-intercept is 0, 7 halves. Our horizontal asymptote is none, because in this case we have the higher degree in the numerator. So instead we're going to have a slant asymptote. And the way that we're going to find our slant asymptote is we're going to do some division. So we have to divide the numerator by the denominator. You can do that using polynomial long division, or you can use synthetic division. To use synthetic division, you look at the x minus 2, and you figure out what makes that equal 0, and obviously that's 2. So that's what goes here. And then you write down the coefficients of the numerator. So 1, negative 6, negative 7. We bring the 1 down. 2 times 1 is 2. Negative 6 plus 2 is negative 4. 2 times negative 4 is negative 8. But this is a remainder, so we don't really care. And our slant asymptote becomes y equals x minus 4. So now we can go ahead and graph that. Because we have zeros at 7 and negative 1, I am going to slide our axes slightly over so that we'll be able to see the 7. So we'll go right about here. All right, we'll make our graph blue. We can put, oh, I forgot our vertical asymptote. So before we graph anything, let's talk about our vertical asymptote. Our vertical is when the denominator equals 0, so x equals 2. Now we have everything that we need. So we'll make it blue, draw on the vertical asymptote, draw on the slant asymptote, graph our zeros, our y-intercept, and then if you need to, plot some other points if you feel comfortable, just kind of knowing that you'll never pass these asymptotes, and so the graphs kind of have to do something along those lines. I'm fine with that. And then we'll write our domain and our range. Our domain is everything but our asymptote, so negative infinity, comma 2, union 2, comma infinity, and our range this time will be all real numbers, because with the slant asymptote, we're not excluding any one y value. All right, let me know if you have any questions.